As you can see from the title of this video, this tutorial is about polarity and what we call intermolecular forces. So for a large majority of the chapter, we've been learning about Lewis structures and how atoms form bonds between each other to lower energy, and how these resulting compounds can have various shapes and sizes and have different atoms within them. Well, part of that leads to the idea of what is called polarity. If you are going to discuss polarity, you have to distinguish between what we are describing. The two types of polarity we're going to look at are bond polarity and molecule polarity. Individual bonds are able to have polarity, right? And what polarity means, right, is the unequal sharing of electrons. So a polar substance has an uneven sharing of electrons. Sometimes you will see this described as an uneven distribution of charge. A nonpolar substance has an even sharing of electrons. Or, like I said, sharing meaning distribution. Bond polarity is very easy to determine. Bond polarity, right, is polar if the two atoms that are sharing the electrons in a covalent bond are not the same, and it is nonpolar if the two atoms that are sharing the electrons are the same. For instance, if we looked at Br2 versus HBr. Br2 looks like this. Right? If we are talking about bond polarity, we are discussing, are the electrons that are shared between these two bromine atoms shared equally or unequally? Well, what determines how the electrons get shared, right, is a property that we learned from the periodic table referred to as electronegativity. I used to say electronegativity measured the hotness of an atom or the ability to attract electrons. Well, if an element has its mirror image across from it, that means they must be able to attract electrons the same so they get shared evenly. If I were to look at something like HBr, you would notice it's very similar, except instead of having Br to a Br, it's the hydrogen. Because hydrogen has a different electronegativity than bromine does, the electrons in this bond will not be shared evenly. Therefore, this has an uneven sharing, making it polar. This has an even sharing, making it nonpolar. And when we're describing that polar-nonpolar, we are talking about bond polarity. A lot of times they'll describe this as a dipole, a bond dipole. And all a dipole is when the electrons are shared unevenly, you'll get a charge buildup. And we'll discuss that when we get into the intermolecular forces. If we're going to talk about molecule polarity, right, we're going to have the same sort of idea. Right? A molecule is polar if overall it has an uneven sharing of electrons, and it's nonpolar if it has an even sharing. A lot of times it'll be described as this. a molecule is polar if bond dipoles do not cancel, and is nonpolar if all dipole moments cancel. So this one is a little bit trickier to figure out what's going on, right? The reason being it's not as simple as looking at what it's bonded to, because sometimes if it's bonded to the same thing on the other side, they'll cancel each other out. So what we'll do is we will try to go through a series of different compounds and decide, are they polar, are they non-polar, all right, and how can we tell? One thing I want you to understand about a molecule dipole or molecule polarity is a molecule is automatically polar if there are dots on the center atom. And what I mean by that is this: if there is an unshared pair of electrons on the center atom, that will lead to an uneven distribution of charge. It will automatically be polar. So this is one of our first checks immediately after we draw a Lewis structure of something, because if it has dots on the center, it's going to be polar. And if it doesn't have dots on the center, we have to look at other things to decide, is it polar or non-polar. So let's take a look at 4 different examples of things like H2O, CH4, NH3, and SO3. So what I'm going to do is I'm going to draw each one of these, and we're going to decide if it's polar or not by saying if it's evenly pooled or unevenly pooled, meaning shared. So if we draw H2O, H2O would look like this. Right? And as we look at this, we would have to make a decision on, is it a polar molecule or not? Well, as I was saying, the first thing I will always check is there a pair of dots on the center atom? Because if there is, it is automatically polar. Well, sure enough, H2O has 2 pairs of dots on the center atom. That makes this unevenly pooled on. Right? The reason being is electrons are negative, so with all these electron dots up here, it makes it kind of negative up here and kind of positive down here, and that creates partial charges. That's what a dipole is, and we'll get into that here in a minute. Right, so, because this has dots on center, that means it has an uneven pool. It is a polar molecule. If I took a look at CH4, CH4 would look like this. Right. First check is, are there dots on the center atom? The answer is no. There's all bonds off the center atom. Now we have to look to see if the things that are off of those bonds will pull on the center atom evenly or unevenly. And remember, what determines how they pull is their identity, right? Where they are. If I slide a periodic table in here, remember our trend in electronegativity. It increases as we go across, decreases as we go down. So if I looked at H, which is up here, and C, which is here, what you will find is that these H's, because they're all the same, will pull the same on the carbon. So you'll have an H pulling this way, this way, this way, and this way. And what happens is this one and this one cancel, and this one cancel because they're all H's. Right? And because they're all H's, right, they have the same electronegativity. This has an even pull on the center, which makes it non-polar. Taking a look at NH3, if we were to draw that one, right, NH3 looks like this. If we looked at that, we go through our check. Is there dots or are there dots on the center atom? And the answer is yes. There are 2 dots right there. Right? That automatically means that the substance is going to be polar. Right? So dots on middle means polar. Right? Last but not least, let's take a look at something a little different. I don't want to do SO3. What if we try CCl3F? Right? CCl3F. So if we do that, and I were to draw it, it would look like this. First question, are there dots on the center atom? The answer is no, there are not dots on the center atom. Right? Because there's not dots, we have to look at the pooling. So what you'll find is because Cl is farther to the right than C is, it's better at attracting electrons. Right? Within this bond right here, the electrons favor Cl. Same thing here, same thing here. Right? And with F, it is to the right. It will favor F, because we know F is the hottest kid at the dance. Right? That means it's the most electronegative. Here's the catch, though. In this example, we had an H pulling up, down, left, and right. They all pull the same. So Cl and Cl here can cancel because they pull the same. However, F and Cl will pull differently because they have different electronegativities. Therefore, this is an uneven pulling on the center atom. So CCl3F has an uneven pull on center, therefore making it polar. Right? And all it took to make it an uneven pull was one of the things being different. Right? Even if this were an F up on top, overall it would still be polar. They won't cancel with each other. Because remember, 3-dimensionally, this is not a cross, it's a tetrahedral. Right? So they're equally spread out. So if 2 of them are Fs and 2 of them are Cls, there'll still be an uneven pull. So if all of the things around the center atom are not the same, it will not cancel out and it will therefore be polar. Throwing one more up here. Let's take a look at SO3 now. So creating some space for ourselves. SO3 would look like this. Right? And then we'd have to create a double bond somewhere. Right? And this would be a resonance structure. Right? But we'll just draw one of the forms. It looks like this. And the million-dollar question becomes, are there dots on the center atom? And the answer to that question would be no. Then we look to, is it pulled on evenly? And you'll see we have an O pulling this way, an O pulling this way, and a double bonded O pulling this way. So the real question becomes, does a double bond pull differently than a single bond? And believe it or not, the answer is no. A double bond and a single bond and a triple bond all pull the same way. They all attract electrons the same way. So if I have 3 O's around it, even if one is double bonded, this is an even pull on the center atom, leading to a non-polar substance. And be careful, I purposely drew these two-dimensionally. Right, and it looks like, well, wait a second, I have something pulling up but not down. If you remember VSEPR, this would be 1, 2, 3 areas with no unshared pairs. It's trigonal planar, which doesn't look like this. It actually looks like this. And now you can see that there is a much more balanced way that they're pulling so that you can see how those bond dipoles cancel with each other. So the big idea with molecule polarity is, are there dots on the center atom? And then if there are not dots on the center atom, is the center atom pulled on evenly or unevenly? Even pull means nonpolar, uneven pull means polar. Alright, so slide that off to the side. Last thing we wanted to talk about, as we set up here, were intermolecular forces. Right? And intermolecular forces tie into what we were discussing right there, because all of the bond dipoles that we're talking about are a type of intermolecular force. So if we're looking at intermolecular forces, there are 3 types of intermolecular forces. And most often I will get tired of saying intermolecular forces, so I will call them IFs. Right? Abbreviation for intermolecular force. Right? First type of intermolecular force are London dispersion. London dispersion forces. Sometimes these will be referred to as van der Waals. Right, named after the person who did some discovering of these. Right, but London dispersion forces and van der Waals forces are one and the same. Right, what types of things get London dispersion forces? Very simple. All atoms and molecules possess London dispersion forces due to something we describe as momentary dipoles or instantaneous dipoles. Now, you don't have to be able to describe an instantaneous dipole. Simply know everything that we discuss always has London dispersion forces. Second type are called dipole-dipole interactions. What types of things have dipole-dipole interactions? Like polar molecules have dipole-dipole interactions. So we'll say that they occur in polar molecules due to uneven sharing of electrons. So if I were to draw for you a dipole-dipole interaction, what I would do is I would choose something that is polar from the list that we just did. All right, so we could do H2O, for instance, or NH3, all right, or something that is of that nature, CCl3F. All right, I'm going to choose something close to H2O, all right, but I'll pick it a little different, and you'll see why in a second. All right, we're going to take a look at H2S. Now, what you need to understand about intermolecular forces is we are not talking about the interaction of one atom with another atom. We're talking about molecule A being associated with molecule B. So we're not talking about if I draw H2S, I'm not talking about anything within this one molecule. What I'm talking about is one molecule interacting with a separate molecule. That interaction. Those are intermolecular forces. All of these things are what they refer to as intramolecular forces. So what I need to do then is account for another H2S. And I'm going to draw that one right here. And the question becomes, why do we see an interaction between these things? Right? And the answer has to do with looking at these molecules individually. If you notice, right, this is a polar molecule, which means the electrons are unevenly distributed. Because there are so many dots on the top, and because sulfur is more electronegative than hydrogen, it creates a partial negative at the top half of this molecule, because there's so many electrons. And at the bottom, a partial positive. Well, what happens is another molecule of H2S comes along, and it's flipped, making its partial positive here, and its partial negative here. And don't get thrown off by that symbol. That's a lowercase Greek delta. That is just the symbol for partially. Right? So delta plus means partially positive. Delta minus means partially negative. And what you'll see happens is we have opposite charges getting close to each other, and opposite charges attract. So what that attraction force is what we refer to as a dipole. Right? So whenever two molecules that are both polar get close to each other, their positive ends line up with the negative ends and create forces of attraction that make them want to stay close to one another. Right? The third and final type of intermolecular force is called hydrogen bonding. And what hydrogen bonding does is it occurs between the hydrogen of one atom and the unshared electrons on an NO or F atom. Specifically NO or F. Right? So, all a hydrogen bond is a particularly strong dipole-dipole interaction. It's so strong, in fact, that they give it a different name. They call it a hydrogen bond. So for this one, I will use H2O because you can see O is one of our three things that can go with hydrogen. So if I were to draw the hydrogen bonding in H2O, it'll look very similar to this. And what happens is we have an even greater partially negative and an even greater partially positive at each location, and that leads to a stronger interaction. And in this case, it is a hydrogen bond. The reason that it is specifically with NO or F, because if you notice, N, O, and F are three of the most electronegative elements that we know of. So what happens is there's a very large inequity in sharing of electrons with those three atoms. Right? So a bond-dipole interaction, and a hydrogen bond are almost identical. The only difference is the dots that are getting shared have to be on an N, an O, or an F with the hydrogen. So H with the dots on an O here, H with the dots on an O here. Just so you get an idea about the strength of these forces, London dispersion are the weakest. Hydrogen bonding is the strongest. Like, that being said, intermolecular forces, molecule to molecule forces, are only about 1/100th as strong as an ionic or a covalent bond, the things that hold H and S together. So this interaction, right, is only worth 1/100th of, say, this bond. So the order of real priority is ionics are the strongest by far, then covalent bonds, then the IFs, and among the IFs, hydrogen bonding, dipole-dipole, followed by London dispersion. Right. So I hope this clears up any issues you may have had with what IFs are and how we talk about bond dipoles and molecule dipoles and the idea of polarity. If you're still having confusion, please come in for some help and we'll get you straightened out.